Right then, I think we'll kick off. Welcome to our 6th Zoom meeting. All the other previous Zoom meetings are actually on YouTube and on our Facebook pages if you want to go and find them somewhere. One day I might actually make a post with all of them in so you can have a look at back ones. I'd like to welcome some new people to the group tonight. We've got Roy, who on my screen is just to the right of me, but I don't know where he is on your screen. We've got John down bottom left-hand corner on my screen. And obviously we've got Ken, who's doing a presentation for us. And Ken's invited Vicky, who, I don't know anything about Vicky at all. Hopefully she's an astronomer of some sort. Or astrophotographer, anyway. And it's nice to see Ant back with us, and Jess. And then we've got the old faithful. We've got Rick, Robert, Bob, Keith, and George is joining us again, as well as Paul, of course. So good evening, everybody. And tonight's Zoom meeting is going to be 2 parts mainly. Firstly, it's the first part's on Milky Way photography and star trail photography by Ken, who very kindly agreed to do it. I'm sure you've seen some of his excellent pictures in our group. And then the second bit is going to be Bob doing something on nebulae. More pure astronomy rather than photography, that one. It will be recorded unless anybody objects, and it will be there for people to go back and have another look at later if you miss any of the things about settings or equipment. If you want to ask any questions as well, we could try out a system that I've never used really, but there's a chat button right at the bottom. If you wanted to actually use the chat button, you could actually put questions in there and we could ask them at the end, which saves interrupting the flow. But I don't think Ken minds if you do interrupt him though. So yeah, Rick's just used that chat feature to say hello. Very quick off the draw. Mark's not here, is he? I just noticed Mark's not here. He's been working hard. We have quite a few people in the National Health Service working in our group, and obviously they're a bit under surveillance at the moment. A lot of things going on. So we hope he's doing all right. Anyway, so without further ado, it's over to Ken, who's going to give us a talk on Milky Way and star trail photography.
Well, thank you for inviting me to give this presentation. It's one that I prepared especially for this session. And I'm not going to claim to be an expert in the matter. I have had a lot of experience, however, and hopefully can give a few tips on the way I started, the equipment we use, and you know, my experience so far. So this opening shot, later on you'll hear me mention looking for Polaris. Well, you don't always need to look at Polaris. This is an example of not finding Polaris, and it gives you a different effect whereby you're seeing the polar north and south rotation direction of the stars. So although sometimes you may want to search for Polaris to create a different effect, it's not always compulsory. So we're going to look at my preferred equipment for untracked Milky Way photography. So the first part, we're looking at totally untracked. We're not using any tracking devices. It's simply a tripod, camera and lens, etc. We'll look at camera settings, including the 500 rule. Location, how important is the location for Milky Way photography? How to make an interesting shot, you know, a little bit of foreground interest as opposed to just seeing the stars, if you like. A little bit on editing. I'm not going to go deep into editing because that in itself is a good hour session, as I'm sure you'll all know. And then we'll look at the basic technique for star trails and editing for star trails. And then we'll have a very quick look at what you achieve when you start tracking Milky Way shots. So this is where it started for me back in 2013. I had a Canon 5D3 at the time, 17-40 f4 lens, and this shot was ISO 4000 at f4 for 15 seconds. Now, the point being, we were just camping on a site. It was down in Cornwall. And I thought, I'll just have a go and see what's about. And this was the result. When you get a good dark sky area, the Milky Way will jump out at you. You'll see stars like you've never seen before. So this was if you like, an experimental shot, one of my very first ever Milky Way shots on a caravan site in Cornwall. So equipment for untracked shot. So a wide angle lens. So my go-to lens is a 16 to 35, and for the Milky Way, I'll usually be at the 16mm end. And there's reasons for that. We'll go on to that when we look at the 500 rule. I'm now on an f2.8 lens. I would suggest that a minimum should be f4. You need, as with deep sky photography, you need to get as much light into there as possible, but you have a limited time to do this with an untracked shot, and we'll mention that in the following slide. Many people even prefer wider lenses, i.e. 11 to 15mm, and that will also depend on whether you have a full or crop framed camera, crop framed sensor. Wide angle lens will allow more of the Milky Way to be fitted into the frame, and it will allow longer shutter speeds without stars trailing. A wide aperture is desirable, and it will affect your ISO settings and your shutter speed requirements. So an ultra wide aperture lens of f1.4, for example, doesn't always make a good Astro lens. So it's best to do a little bit of research before making a purchase. And the reason I say that is I had a Canon 24mm f1.4 L series Mark II lens, and it gave an effect called coma on the stars. It was a really awful effect and just no good for astrophotography. So do a little bit of research and read a few reviews before you actually make a purchase. Another thing to consider, and I think this is something that Martin's experienced, is that in the 11 to 15mm range, you can get a lot of distortion. So once again, bear in mind, do some reviews and make sure you get the right lens for the right job. A good sturdy tripod. You're never going to hand hold a Milky Way shot. You're going to be looking at shutter speeds anything from 10 to 30 seconds. A remote shutter release, or use a 2-second timer to release the shutter so you're not getting any shake. Lighting. We'll show you an example of why you may need some lighting with you, either a torch or a flash unit. You may require to illuminate the foreground subject. The light pollution filter. Not something I've used, however, I do know that people have them. I believe somebody has one in this group, and they're supposed to be very effective. It's just that I've never used one. So as for the camera, I have a full frame and I've done for many years, but some of the modern crop sensor cameras are perfectly capable of giving low noise at high ISOs at long shutter speeds.
You know, the light pollution filter, Alan Wallace,
Yeah.
he produced one, hasn't he, in the last 12 months or so? I can't remember what it's called now, but you know.
I know there have been a few out for quite a while, longer than 12 months.
Yeah.
How effective they are, I'm not sure. I think they're supposed to cut down on tungsten light pollution. I've never used one, so I can't really comment on that. They may well be good. Once again, the best source for that type of thing is to read a few reviews on them. So I wanted to show this one, an example of two different things, really. First of all, you're seeing the effects of light pollution in the distance. This is a tin mine over the Cornish coast, and that's St Ives in the distance. So down to a certain height, you've got a lovely detailed Milky Way. But once you get below, nearer to where the town is, then the light pollution will simply just make your Milky Way diminish. So light pollution is, very important. Dark skies are perfect for Milky Way shots, whereas light polluted areas, it may wash the Milky Way out a little bit. Now, the other thing about this shot, I mentioned lighting in one of the previous slides. If you can see a small stone pillar just in front of this tin mine, I'm actually hidden behind there, and I'm lighting the tin mine up and the stone face using a torch. So it's a basic torch. I'm hidden behind there, so I'm not in the shot. Obviously, set the camera to a timer, and I've illuminated the building and the stone face there. Without illuminating that, it would be pitch black. You'd see nothing. So be prepared to illuminate subjects to make them look more interesting. So camera and lens settings. As with deep space astrophotography, the more light you can collect, the more detail you can reveal. Invariably, therefore, good dark sky locations, you'll be using high ISOs, 3,200 to 4,000. Remember, these are not tracked shots, so you have to gather the light. And you should be using shutter speeds up to 30 seconds. So these are for single images, without blending separate images. And don't be too disappointed if you get some digital noise. Obviously, the better camera they have and better sensor, the more the noise can be controlled. But you can expect some digital noise in the images. Use mirror lockup, unless you're on a mirrorless, of course, and either remote shutter release or 2-second timer to prevent camera shake. For the majority of my images, I find that settings, the lens to manual focus and infinity works well. So usually, whether you're a Canon shooter or a Nikon shooter, you do have a mark on your lens that dictates infinity.
What can I just ask? Sorry,
Yeah.
what if you don't have infinity on your camera?
If you don't have infinity, one of the methods you can use is to focus on a distant light, or even point your camera at a bright star and get that sharpened in focus, and
Right.
then switch your camera to manual focus.
Okay.
You should get a similar result. Okay. Use the widest aperture available. So if you've got an f2.8, use f2.8. If you've got an f4, use your f4. And don't forget, if you're on a tripod, turn your image stabilizing off. You don't use image stabilizing when you're on a tripod. For white balance settings, I find that either I put WB there. That should be auto white balance, sorry, or tungsten will give you a good starting point. Particularly if you're shooting in RAW, then you can make all the adjustments you want. Just be aware that if you're shooting in JPEG, you have less adjustment in processing because you can't alter things like white balance as easily. Now, we mentioned shutter speeds and the 500 rule. Now, the 500 rule is a guide to how long your shutter speed can be before stars trail. So if you can imagine, whilst and you know this from your deep space astrophotography, when you're doing deep space, you have to use your guide on Polaris so that you mimic the rotation of the Earth. And it's the same with Milky Way photography. if you have too long a shutter speed, your stars will start to trail and your image won't be very good. So the basic formulation is 500 divided by the focal length of your lens. So as an example, if you're on a 16 millimeter lens, you'd be 500 divided by 16, which would give you a maximum shutter speed of 31 seconds before those stars begin to trail. So you can see now that you've only got, in that instance, 31 seconds to bring in as much light as possible, which means invariably you're going to be using high ISO. And remember, if you, on a crop factor camera, a sensor, remember that you have to add that into your equation. So on a crop sensor body, it would be 16 millimeters multiplied by 1.6. So that would give you 25.6 millimeters. So if you're on a crop sensor, you want to be looking at a lens in the region of 10 millimeters. So you can therefore see an advantage of using wider angled lenses to interact images. Some slight star trailing won't be noticed in a wide field image, unless you're really pixel peeping. So some degree of star trailing would be acceptable. You wouldn't really notice that. So location, location, location. Always very important when you're taking Milky Way shots. This is one that's within reach of all of us. This is at Ribblehead Viaduct. I presume most people know where that is. You can get very, very good detailed Milky Way shots at Ribblehead. And perhaps in the future, we should consider a group excursion out to Ribble and see what we can all achieve.
Are you offering to lead a party then, Ken?
By all means, yes. By all means, once we get this dreaded COVID out of the way, I'm more than happy to do that. Absolutely. There's also some safety in numbers there, isn't there? I know I've been out many a time on my own in the middle of the night, and you can frighten yourself easily. You never know who you're going to bump into, do you? So there is some safety in numbers as well, going out and doing nighttime shots. So what is the ideal location and time? So dark sky areas are a must for decent Milky Way shots. I'm not really into I know you guys have been looking at the portal measurement of the skies around where you live. I'm not really familiar with that. Needless to say, you need to be in a really dark location. You're not going to get a decent Milky Way shot on the outskirts of Manchester, for instance. I've tried it, but it's just impossible. There are quite a few regions around the UK. So we've got Cornwall, Dorset, Anglesey, which is another area I'd love to visit, Anglesey, to do some night work. The Lake District, Yorkshire, North East England, Scotland, some of the more remote areas of Wales. And I've never been, but probably the Peak District, I would imagine, is quite dark. I know Vicky is more familiar with that part of the country. I would imagine some parts of the Peak District are going to be very good for dark skies also.
There's a specific place in the Peak District called Surprise View. I don't know if you're aware of that one.
No, it's not an area I've ventured for Milky Way shots, but it's I can imagine you've got quite a vast expanse looking to the south there, and it'd be certainly worth a try, yeah.
Yeah, definitely.
Yeah. And the best time of the year, usually late spring through to late autumn, and that's when the Milky Way is more vertical in the sky, like you've seen in some of the shots. If you go out in the winter months, the Milky Way will be sort of laid down nearer to the horizon, and it's more difficult to get a shot unless you're in a really, really dark sky area. Some of my shots were in midsummer. However, you only have to, in the summertime, you only have a small window between around about midnight and 2 a.m. So it doesn't get properly dark until about midnight when you're in the summer months. And round about 2 a.m. it starts getting light again. So you've got a very limited window. You've got to time these things almost to perfection. And the best view of the Milky Way is always south-facing. That's where all the interest is. Always avoid half to full moon. That will, as with your deep space photography, it will just bleach out the sky and you'll see very little in the way of detail. Foreground interest, for me, makes an image far more interesting. So we've got two different shots of the Milky Way here. One of them on the right there is just the Milky Way. And yes, you've got one or two meteors in the shot there. But I think the shot on the left for me is far more interesting. You've got a little bit of foreground interest in the rocks. You've got a view across the bay. And once again, this one is Cornwall, a good dark sky area. And once again, the rocks, I had to illuminate those myself to bring that little bit of interest.
Ken?
Yeah?
When you illuminate it,
Yeah.
can you just wave the torch at it, or do you have to keep the torch on it in one position?
No, invariably, when you're, let's say if you've got a 30-second exposure, you literally just flash the torch over it. Or you can use a flash. I quite often use a flash. And
but you can move the torch around then to light up different parts of the rocks.
Oh, absolutely. You can do what you would refer to as a bit of light painting. Yes. Yeah, you can do all sorts of improvisations and experimentations to get the shot you want. But the main thing is that you've got a source of light with you.
Yeah, and is that that photo in Cornwall that you just showed?
Yeah.
That light pollution on the horizon, or is it just the Milky Way going a little bit red with the thicker atmosphere? It's very close to the sky, isn't it?
I believe that's just a little bit of the atmosphere as you're coming down to the horizon there. And right in the centre of the frame there, I believe that's a boat out at sea.
Yeah, it's a lovely shot, that. Absolutely.
Yeah.
Classic.
Does anybody know what's it called? You know, when they get it in Wales, when the sea, the waves at the shore, they go phosphorus blue at night.
It's called bioluminescence.
Every year at a certain time.
Yeah, bioluminescence, and you get it. I forget the name of the lighthouse there.
Penmon Point.
Which one? Sorry.
Penmon Point.
That's the one, Penmon Lighthouse. You get the bioluminescence, and it's also a great area to catch the aurora. The only problem with the aurora, as we all know, it's very infrequent, and for me to get there and guarantee seeing an aurora all the way to Anglesey, it's a little bit of a trek to not get anything. So
yeah,
it is a great one.
Bioluminescence with the Milky Way, that'd be some shot, wouldn't it?
Well, that'd be fantastic, wouldn't it? I'd be happy for the bioluminescence. I've not managed to get that one yet. So editing, I'm not going to go deep into editing because, as you know, we can spend a good hour on editing on its own. With Milky Way shots, it's important, but far less demanding, I would say, than what some of you are used to with your deep space editing. So I'm not going to go in depth. I'll leave the link on here because this presentation, it will be available should any of you want to use it or go back and refer to it. I'll leave a little link here to a guy who, just showed you some basic Milky Way editing techniques. If you want to go on there and have a look, it's a good starting point, shall we say. Okay, so we've done the Milky Way, we'll just talk a little bit now about star trails, because it is a little bit different. You don't need special equipment for star trails. Your focal length is less important because you actually want the stars to trail. Lower camera settings can be used because whereas you're looking at maybe ISO 3200 to 4000 to get detail in the Milky Way, you can actually see the stars with as little as ISO 800. It's quite often adequate. And all you're wanting are the stars. Once again, for me, foreground interest will make a better image, and lighting up the foreground in at least one of your frames is likely to be required. So let's say if you're taking an hour's worth of frames, you don't need to light up every single one, because when you go into editing, you can just use the one shot that you've taken where you've illuminated the foreground. The main difference is that you'll take a series of images, minimum of an hour, I would suggest. You can take 2 hours, it depends how much time you've got, but with as little as 1 hour's worth of images, blending them in post, you can get a good star trail. So it's useful, therefore, if you could have an intervalometer. Some of you may have one built into your camera. If not, it's useful if you have an external intervalometer that you plug in. It will just save you standing there taking image after image. You can walk away and let the camera do its exposures while you do something else. Now, the other thing I wanted to mention on there is that there are useful free programs for blending your images. So if you don't already have Photoshop or something like that, there's a free program called Star Trails X. It can be downloaded, and it's quite a useful tool. You can save all of your images into a JPEG to make it quicker and easier, so you've not got a massive file size. And using this Star Trails X, you can also create time-lapse footage of your stars actually moving. You get the option in there to either create a star trail or a time lapse of your stars moving, or you could do both. The only thing I would say is that to do a time lapse video, to get a good one takes a hell of a lot of more images really than a simple star trail. Maybe where you would take a minimum of 1 hour for a star trail, for time lapse you may have to take a minimum of 2 hours. Okay.
Can I just say something, please?
Yeah, sure. Yeah.
If you're using a tracking mount, the star trails will be a lot less time if you speed up, say, times 24 or something, or even put north to south on your tracking mount.
Yeah, that's true. If you reversed it and did north to south, you can cut down on that a long way. Yeah, absolutely, agree with you. Yeah. Yeah, if you can find an easier technique such as that, then all well and good. And I'm just giving you the basic methods here.
Yeah, it's just another alternative, that's all.
Oh yeah, absolutely, absolutely. What I tend to do, to be honest, I usually have 2 cameras with me, and I'll quite often set one camera going and go on while that's taking its shots, I'll go and do something else with the other camera. It's either that or you have to sit around waiting, but yeah, you can speed up the process, as you said, with your tracking device in reverse, so to speak.
I think one of the points of this is though that you can actually do this with a minimal amount of equipment. It just takes longer.
Yeah. Well, that's right. This is the basic sort of taking the photos.
That's a fantastic shot, that.
So this is Darwin Tower. Once again, it's not a million miles away from us. We can all reach this. There's probably a couple of hours worth of images here. And once again, the tower was illuminated, and I'll demonstrate how shortly. In this one, we've actually found Polaris. You can make an interesting effect if you've got a subject pointing to Polaris, and basically you set your camera going and walk away and leave it running.
So are we stacking these images, or am I being a bit daft asking that question?
No, these images are all stacked. So that's
They are stacked.
Yeah, if you go back to the previous slide, this free program, Star Trails, it will stack them all for you. Once you've done your
right, okay.
Once you've done your
so
basic.
We can't do it in so we can't do it in Deep Sky Stacker then.
You wouldn't do that one in Deep Sky Stacker, I don't think. No.
Right. So I'll download this Star Trails app then. Right, brilliant, thank you.
If you have Photoshop, you can do it in Photoshop, but this is, if you like, the bare basics for what you would need. If you haven't got Photoshop, and not everybody has, then you can download the free program and it'll do it for you. Okay.
Yeah.
I mean, if after this presentation, in the future, if you're ever doing Star Trails and you need any tips or advice, please ask.
Ant seems to be in California.
So if you're seeing all this, then apologies.
Just well, look, that's downloading. I was watching that Trevor Jones last night, and he was a software program called Sequestrator or something like that, and that actually froze the your foreground. Because what you used to do is take your foreground, and then take your Milky Way and blend them in Photoshop.
Yeah.
But this actually froze your foreground for you.
While it's downloaded, could I just welcome Chantal? I didn't realise that was you at first, but that's you, isn't it, Chantal? Shani B.
It is, yeah. Sorry. I've come into the group about 10 minutes late. I've been at work, so you would have heard me rattling around with my keys and locking doors and stuff. And now I'm actually just driving home, so you're on my what do you call it? Loudspeaker in my hands free, yeah.
Got you.
But I'm home in a second, so I think I'll just park up on the in the car, and I can hear you better from the car, you see, than just my phone.
Okay.
Right, it's not doing it. So what I wanted to show you there, 'cause for some reason that link's not working. I wanted to show you the same shot, but you would actually see the stars rotating around the tower in a video. So that would be what you would call the time lapse. You can do it with the same program, the Star Trails. Okay.
Well, we'll have that on the Facebook group, and I'll copy the link out so people can see it as well.
Yeah, I'll add that to the Facebook group when we've finished. Okay, so we've done Star Trails. Once again, any questions in the future, anytime, please ask. Just talk a little bit about tracked Milky Way shots. Once again, you don't need special photography equipment. However, you would need a tracking device. So you need to track and stack the images, similar to what you do for deep space. So I know most of us have a tracking device of some sort. Obviously, if you're going out to do a Milky Way shot, it's not easy carrying a HEQ5 with you. Ideally, you want one of the smaller, more portable ones. And blending of images.
Can I ask a quick question? Sorry.
Yeah, sure.
Does my EQ3 mount have a tracking on it, some sort of guiding, or is it not? I'm getting a bit confused with John. John says that he's got something that's guiding, but then he's bought extra that he fits onto his mount. But I don't have that, so do I still have some sort of tracking?
I think in answer to what you're saying, and maybe John could answer it better, but I think What John's talking about is
mount.
what John's talking about is a device that he links up to his computer that actually, via a gyroscope, helps you to track a particular object, and that's different to having basic star track, polar aligning and
tracking and guiding are two different things.
yeah.
The mount tracks, but to do guiding, you need a second scope and a second camera, and that just tries to keep the tracking more accurate. But we often do say the wrong word when we say guiding when we mean tracking sometimes, and tracking when we mean guiding. But
I think that might be what happens.
Yeah, your mount will track, but not guide without a second scope.
Okay, right.
Okay.
So it's fine for this.
Oh yeah.
Right.
Okay. It'd be good for tracked Milky Way shots. Yeah. So in this instance, you have to take at least one image without tracking, without going into different programs that people may have invented. I know there's all sorts of things out there, but for basic shots, you'd need to take at least one image that isn't tracked. If you can imagine, if you're trying to track the stars, you can't track the foreground image as well because it would just be blurred. You're actually moving. So you take one that isn't tracked, and then you can blend the two together. I'm not going to go deeper. I just want to give you an example of the type of difference that you can achieve when you start tracking the shots. So here's a photo. So the basic message is that when you start tracking Milky Way shots, you can use any focal length you want to get the Milky Way as large or as small in the shot as you want. And you can bring out a tremendous lot more detail. You can bring out far more detail than a single image. So if you have a tracking device, and certainly that's my next way forward is using tracking. I'm going to start doing some track shots, try to improve what I'm achieving, and bring out more detail in that Milky Way. Okay. And that really is the end of the presentation. Does anybody have any further questions? I'm sorry that I was unable to open those links. It was just a couple of examples I wanted to show, but for some reason it's not letting me open those links whilst we're in Zoom. So
Not to worry about that. The links can be made live on the Facebook page anyway.
Yeah.
It's all a bit of a learning experience trying to use Zoom and do presentations. What I tend to find on the whole is it's best not to rely on anything live off the internet while you're doing it, and try and download stuff prior to doing it and then have that. But that's just something, it's not lost anything for it, because we can go and have a look at the link after this session. Has anybody got any other questions?
I had a quick one, Ken. So I know that you said you weren't going to go into the processing side of things, but just generally speaking, how do you blend the foreground and the stacked sky image?
Well, there's probably a few different methods. Are you using Photoshop?
Yeah.
Yeah, Photoshops, you can usually do it by overlaying one image over the other, and then brushing out the area that you want to change.
Yeah.
Or you could probably overlay and just change the sky. There's probably a few different ways in Photoshop that you can do that. Probably the easiest way, because it's going to be the same image virtually, is overlay them and brush out the ground area so that it then reveals the untracked version. But there's probably a few different ways you can do it, particularly in Photoshop. I would imagine it's very similar to when you're doing your deep space photography, though. There's probably lots of different methods you can use, and it's just a question of learning those techniques, isn't it?
I do know that one of the Mac programs, which I think is called Starry Landscape Stacker, it's not a free program, unfortunately, and I don't have it, but it does actually separate the foreground from the sky for you automatically, and it will be using masking to mask out the foreground and then apply the background to it.
Yeah, usually select the foreground. You select the foreground because it's usually in shadow. Then you delete the sky. So you've just got your foreground with a transparent top. And then you put all your sky images underneath. And then so you have a stable foreground and your sky changes. So you select, if your foreground's black, you can select it and then delete the sky and put in what you want over the top.
It's just getting that edge, isn't it? The edge, the blend between the actual foreground and the sky to look good.
Or you can do a little blur brush then if you need to.
Or feather it.
Yeah. Or you can do a graduated mask, of course. You can do an overlay going from black to white, and then it does a smooth transition.
Yeah.
Yeah, there's a few methods you could use. Really, tracked Milky Way shots are the next step for me. I've not done very much on that side of things, but it's certainly something I look forward to doing more of because of the detail that you can bring out when you do that.
Well, I'm certainly up for a trip to the Ribbleheaded with a party, and like you say, it is better to go in a group. We've always said that, really, at least two of you or more, because you never know what's going to happen. You can fall down a hole in the dark somewhere.
Well, that's absolutely right. Yeah.
I just get mugged by sheep.
I was once on the top of the cliff doing that wheel coach mine in Cornwall, and I could see two torches coming towards me. I was on my own, and you start thinking, who could this be? What shall I do? It turned out they were there for the same reason, but you just never know who you're going to bump into, do you?
No, I mean, one night I bumped into John Walsh. That was a scary thing.
Yeah, it would be, wouldn't it?
That place that you were talking about in Wales, is it called Puffin Point?
Yeah, it's a Penmon Point. Penmon. But Puffin Island is across the...
Puffin... Right. Is it? You have to pay to get in?
No.
The guy who lets you in,
That's
pay
right.
$5 or something to get in.
Yes, you do officially, unless you sneak in late.
Well,
we did go there. It was horrendous weather, so I'm a bit gutted about that. I got a picture of the lighthouse just before it thrashed it down.
Yeah.
Yeah.
And that's where the bioluminescence is there as well. And I noticed that Vicky gave us a link. Vicky? Vicky gave us a link to some bioluminescence site or page.
Yeah, there's a guy called Chris Williams. I think he lives in Anglesey actually. He's got some fantastic pictures of the bioluminescence and Milky Way and a few other things. So if you're interested in it, it's worth having a look.
Yeah, he gets the aurora up there as well, doesn't he?
Yeah.
Yeah, he's got some nice shots.
The shot for me, which I'm trying to get one of the locals to take me to, because you're walking in the dark and you want to know where you're going. But it's the shot on Llandwyn Island, which is on the other side, which is by Newborough, where you have the church and you have the cross and the lighthouse, and you see some astounding shots.
That's on my to-do list also.
But you have
definitely
to go,
on my to-do list.
Yeah, you have to know the tides for one thing, because the island gets cut off, so you could spend all night over there. But it's a fantastic location for foreground interest, and I think it's the trip we'd like to do to that, as well as to Ribblehead as well.
I'm sure there's lots of places. The only problem is the further you travel, you've got to make sure you've got a good chance of a clear sky, and that's the only thing you need, isn't it?
Yeah.
Like for me, Anglesey is going to be a good 2 hours. So if I'm going to be 2 hours there, 2 hours back, I want to make sure I'm going to have a clear sky when I get there. Really.
Yeah.
It's like over here with the Peak District. I mean, I've left my house and it's been, quite clear. I've got over there, it's a bit cloud or fog, low mist or something. And that's
Yeah. And you will have wasted trips. That's part and parcel of the astronomy and photography. You will have times when you visit these places and it'll suddenly be misty or something like that, or cloudy. That's just, you have to keep going until you get that shot.
It's why it's good being a birder as well, you see, because you go out and you do your birding during the day, and then you stay on to do some night photography. And if it actually isn't so good for night photography, you haven't wasted the day.
Yeah, well, I'd be up for that as well.
There's about 4 of us here will agree with that.
Yeah. Yeah, definitely do that.
Can I ask about Sequator? Because I've downloaded that and I did read a couple of forums and they kept on bringing up Sequator. So I thought, well, I'll download it whilst it's in my head. But I actually don't know how to use it. I don't know what it's used for. Is it for deep sky objects or is it for star trails or?
It's for Milky Way. It's for Milky Way photography.
Right.
But if you go on to Trevor Jones' Astro Backyard, he's got a really good tutorial of it, and he's only recently put it on as well. So
something I've not used. What's the advantage of that, Peter?
I think isn't it one of these things where it'll do the foreground for you.
Oh, is
yeah,
that
it freezes the foreground. That's a good thing. It also drives to Anglesey for you as well. Comes back.
Sorry.
What does
that mean? What does that mean? Raises the foreground. I know I'm sounding daft now. What does that mean?
If you just take it, you say there's some trees or something and rocks. If you just take the image, the rocks are blurred, because obviously it's really soft because it's a long exposure. So the normal way of dealing with that, it's quite easy, is layer masks in Photoshop. You take an image of the foreground and then you take your image of the Milky Way and you just blend in with layer masks your foreground. But this software package removes the need to even do that. It can freeze you. I don't know how it does it, but in stacking, it can freeze your foreground. You just paint over the foreground you want to do in the software, and just stack it, and it freezes it for some. I don't know how it does it, but
I think it might be more to do with exposure than freezing it, because most of your foregrounds will be rock solid anyway, won't they? There'll be rings or stuff.
Yeah.
But the exposure will be wrong for both of them, so you have to blend 2 exposures, one for the foreground and one for the sky, and that's
well, you do unless you're able to illuminate the foreground.
Well, yeah.
If you sort of a bit of light painting, you can bring all sorts.
Yeah.
And one of the things we noticed at Ribble Head is if you got the timing right, you just waited for a car to go past, and it illuminated all of the viaduct. And then that's one with all the detailing for the viaduct. So you can illuminate big areas if you need.
Yeah. There's a guy in the Heaton Park group called Pete Collins, who is quite big on Milky Way in that area. And if you look on the Heaton Park Facebook group, you'll find lots of his shots of the Ribble Head and that area is North Yorkshire. And he gives talks now and then. I was thinking we might actually get him to give us a talk at some time in the future. Right, well, shall I say thank you very much, Ken? That was really good talk, and thank you for allowing us.
We're all still awake anyway.
I think what we can do is we can actually say, if anybody thinks of any questions afterwards, we can put them into the Facebook page under the file, and then hopefully Ken will have a look at them and answer any of them.
Well, there's obviously a lot of people in the group with knowledge, on all different areas, whether that's editing or, so I'm sure, any questions can be answered between all of us, can't they?
One last thing I'll say about it is I went up to Islay in Scotland in September in between 2 lockdowns, and I was going for Milky Way shots, was one of the things to do, as well as the wildlife. And I was astounded at the amount of light pollution from Northern Ireland that actually got on my shots.
Right.
And yet most people, when they look at them, just think they're sunsets.
I'll be doing my thing in a minute, honey.
So it's not always that bad a thing.
That's not a problem anymore, though, Martin, because there's a border in the Irish Sea now.
Needs
You need an export license for the light pollution. Yeah.
Anyway, nice to see you, Chantal. We can see you now. You're sat in your car. All the neighbours,
Yeah.
what the hell's she doing?
Yeah.
Only like any other day. I'm just in the car instead of outside.
And Dane's joined us as well.
Right
He's put the kids to bed. So nice to see you, Dane. Dane is our beard meister. I think he's short. Have you cut it, Dane? It looks a bit shorter.
I trimmed it about 2 months ago.
Right.
There you go.
Well noticed though.
Yeah. Well, it normally goes off the bottom of the shot. You can see the bottom of it. Okay, so thanks very much, Ken. Brilliant. We'll look forward to having the PowerPoint there. And hopefully we'll get out on a trip with you at some point when things allow.
Yeah, that would be good. Fingers crossed for all.
Yeah. Cheers, mate. So I'm going to move over to Bob now, Robert Stewart. Bob. And he's going to give us a talk on Nebula.
That's right. If you're not all asleep by the end of the first slide, I failed miserably. Okay. Hang on then, let's see if we can get this
Have you
up
got
and running.
screen sharing?
Yeah, hopefully. Yeah.
Hang on a second. It's gone dark in here. It's gone very dark.
Yeah, share screen. Oh, I've got nothing. Hang on a sec. Let's try that again. I'm not going back to the meeting. I'm not doing anything. Let's try that again.
Might move into the house whilst you're setting up.
Okay.
It should be. Is it me or what? Share. Hang on.
Well, I've got you on sharing, and it went blank screen.
So I've got desktop 1. I don't normally usually share.
Ah, have you moved it off the side of the screen?
No, I don't think so.
I saw a bit of the image then just disappear off the right.
I seen a little bit as well.
I seem to want to go slow here.
Do you switch between screens on your Mac?
I didn't think I had. No. Share screen. That's it, isn't it? Yeah. That's what usually happens. We're obviously going to have.
Right, keep trying.
I want desktop 1, really, don't
you? What you want to share?
It's usually desktop 1, isn't it?
That's on a Mac.
Whiteboard,
You're talking about a Mac.
Yeah. Well, it's got desktop 1, which I can see you. I've got keynote. Oh, hang on. There we go. Share. Bingo.
Yes.
Yeah.
I've forgotten. I got it already. Sorry. Yeah. And that's not the first slide. There we go. Can you all see that? Hopefully.
Yeah.
Yeah.
I'll do that as well. Right. Nebula, come in all shapes and sizes. Are you still with me?
Yeah.
Yeah.
This is just a small portion of umpteen thousand planetary nebula. And as you can see, every single one, totally and utterly completely different. And we'll be discussing planetary nebula as we go along, but they've only just kind of worked out why they all look different. But that's a 4 or 5 hour lecture all on its Todd.
It looks like it's shot down a microscope, that.
Yeah, all the protozoa plankton. Yeah, some scary ones. The Eskimo Nebula, the Ring Nebula, Eskimo Ring, things like that. Yeah. The I think that's a cat's eye in it, but different. Oh, hang on a second. Now what have I done?
You zoomed.
That's it. Thank you. Hang on.
Bit more.
I'm going back to bed. Right, basically, as I was going through this, I found out that as I was sort of trying to map a logical path through the types of nebula, as you go through the types of nebula, you're actually mapping out the age of the stars as well. So you're going through basically the star's life cycle pretty much. So they all sort of key in rather nicely. Right, basically, although nebula come in all shapes and sizes, from small at a light year or so across, that's a typical planetary. How many people thought that a planetary would be kind of tiny? Can you hear? Yeah?
Yeah.
What did people think the average planetary nebula was in width?
Well, you'd think it was a small one, wouldn't you?
Yeah, sort of like out to the Earth cloud or something, wouldn't you? But
Yeah.
not a light year. I was quite surprised at that. To hundreds of light years across, star-forming regions, and supernova remnants, because the Vela Nebula, the Veil Nebula, are all hundreds of light years across now. Obviously, they started off small and have got a hell of a lot bigger. All the nebulae you see are visible for basically 3 reasons, so that narrows it down a bit. The first lot is they emit radiation due to ionized gases, and they're self-explanatory. They're called the emission nebula. The examples are the Helix Nebula, the California Nebula. The second set of nebula, they reflect light from nearby stars. Once again, self-explanatory. The reflection nebula, the most well-known being, of course, the Pleiades, which are also known as the Seven Sisters. And if you're in Asia, they're called Subaru. And that should ring a bell with somebody. But the car manufacturer, and their emblem, of course, on the bonnet is the Pleiades. And then the third is basically the obscure light. So you have a light source, either emission or reflection nebula, and then you have basically dirty grey clouds of dust and gas, and these appear as a silhouette against a brighter background, and they're called dark nebula. And of course, the most famous of these is the Horsehead. It's Horsehead to us. It wouldn't be a Horsehead to anybody else. Any other aliens would see it totally differently. So, and although these look bright and spectacular, some of them at least, to the naked eye, and although they are denser than space around them, they're still very much thinner than even the best vacuum here on Earth. And the quote was, a nebula the size of the Earth would have a mass of just a few kilograms, which is pretty vacant. And though there are 3 classification systems, the reality is that most nebula are actually a combination of all 3. The Trifid is a wonderful example of 3, and this is the Trifid, so-called because it's divided into 3. And there's the reflection part of the nebula. There's the emission part of the nebula. And the dirty great dust lanes across it are, of course, the dark nebula. And the Horsehead is 2. It's an emission nebula behind the Horsehead. And the Orion Nebula is a combination of all 3. And we'll obviously discuss these as we go along.
Is the Rosette Nebula similar to that then as well?
Yeah, because it's got the Bok granules in it, and it's got the emission nebula, and then of course it's got a whacking great. I don't think there's much reflection in the Rosette or the Helix. I think they're all. There's not a lot of dark bits in it, just the odd occasional Bok granule. Right, and although there's 3 reasons for them being visible, they're divided into certain types, and this is the cultural part of the show. How many people have heard of Herbig-Haro objects?
No.
Yeah.
But they're quite interesting. I hadn't realized that theoretically amateurs could actually photograph one. When stars are first forming, they obviously get a massive dust cloud, and it all condenses down, gravitational collapse. And eventually you end up with a very hot ball of gas. But it's not quite hot enough for nuclear fusion. The gravity and density isn't quite there. So you've got an exceedingly large, very hot ball of gas that's trying to become a sun. It keeps failing. It's about to start your car, it goes ch-ch-ch-ch, and then fails dramatically. As soon as it tries to get some sort of a nuclear reaction going, it puffs, and as soon as it puffs, the engine stops. So these things are very, very unstable, and they are emission nebula, but they're not emission nebula because the gas has been excited by intense radiation. They're emission nebula because the gas has been stimulated by muck and bullets traveling at exceedingly high velocities as the protostar ejects clouds of dust and gas, which funnels out usually from the polar regions at hundreds of thousands of kilometers a second, hundreds of kilometers a second, and plow into the surrounding dust. Net result is you get superheating, and that causes the emission. So it's not by radiation, it's by physical impact. So that's an important difference. And we've got another I've written down here, Herbig-Haro objects. These are bright patches of nebulosity associated with newborn protostars. T Tauri was the first one discovered. And if you have you heard of the Hertzsprung-Russell diagram? It shows the evolution of stars, gas giants.
Oh yeah, yeah.
Yeah. If you look on a Hertzsprung-Russell diagram, if you look over into the extreme left and up a bit, you'll see T Tauri stars. And then they start in the top left-hand corner. And as they gradually drift down to the mainstream, as they become stars, but they're not stars as they are. They are found in star-forming regions. They're only a few million years old, so they're very young, and are having a tantrum, basically, as their stellar engines settle into some sort of routine. At the time they are large in radius, their surface temperatures are actually quite low, only 4,000 K or lower, much lower, typically 2,000. And the core has yet to reach the temperature for hydrogen fusion to occur properly. It has fits and starts. Occasionally, there'll be a little bit of a nuclear fusion, and it immediately blows itself apart, so it stops. So the stars all over the shop. The patches, the illuminated parts, are formed where jets of partial ionized gas ejected by the star collide with the surrounding gas at several hundred kilometers per second, so they're shifting. They tend to be within about a parsec, 3.26 light years, but some can be found even farther out from the parent star, depending obviously the energy and the size of the protostar. Oops, done it again. They're actually observed in the 19th century, so lots of these things are quite old, have been known for quite some time, but of course not known what they were. But it wasn't actually until 1940 it was understood what they are. So that's only 60 years that we had a handle on what we're looking at. They are transient objects lasting just a few tens of thousands of years. Many are invisible except in infrared, as they are still embedded deep in the gas and dust surrounding the star. And they will become visible when the envelope is blasted away. The pillars of creation are an example of where the dust has started to be blasted away. So you can see the star, and underneath you can see the gas. And apparently they now reckon that the pillars of creation might not be there anymore because they think a couple of the stars have shown early signs of going supernova. So in about 10, however far away the Eagle Nebula is, in a few thousand years, all of a sudden, the pillars of creation will be toast, and we won't see them anymore. This is a picture of a Herbig-Haro object. It's called the lightsaber. Can you see that one? Hang on. There you go. Hang on. Let's do it again. Yeah, it's called the lightsaber, for obvious reasons. That's a Hubble telescope view. The star that's causing the troubles is behind here, and those are the polar regions, and that's the jet of gas, well, just of dust and gunge that's been ejected, and it obviously impacting with the surrounding gas and illuminating it. It's actually visible by the M78 nebula in Orion. So this one, in theory, we should be able to photograph. It would only look tiny. It would be like a little light stalk. We wouldn't see in this much detail. The nebula are variable over a timescale of a few years because they change. HH24 is a class O protostar. Do you know the sequence Obia Fine Gill? which is the star. O and B are all very blue, going down to us, main sequence. Well, O is the beginner of it all. So they just starting off and there. And it's these stars are not on the main sequence of the Hartsprung-Russell evolution graph, but our sun is. So anybody who images M78 anytime soon, might see if they can find that. All clear so far? You all still awake?
Yeah.
Oh, see, I failed.
Can I just say that I saw a quote on some Facebook group about the Horsehead Nebula the other day, saying, the question was, he said, which part of the horse's head are we looking at? And I thought, is that a trick question? No, sorry, which part of the horse are we looking at?
Yeah, clearly, yeah, is that like a camel formed by a committee or something like that? Yeah. Right, the second lot then. So having moved on, so the Hubble objects, the new stars, will eventually go into the main sequence, start to blow all the dust and gas away, and you'll actually see them as stars. And this is the realm of the emission nebula now.
Bob?
Yeah?
Just explain for the benefit of all of us what the main sequence is.
Yeah.
No, I mean in a sentence.
In a sentence. Oh, thanks. Yeah. Basically, the main sequence is the luminosity. Hang on, I always get this wrong. It's the luminosity of a star versus its temperature. And as a star evolves, it comes down from what are called a protostar. It gets smaller and hotter, and its temperature rises, and its what was I say? And its luminosity increases. And our sun is in the middle of the main sequence. Actually, see if I can find one.
No, it's basically the life cycle of a star.
Yeah, that's right. And stars like our sun go along the main sequence. They go from where they are now, a normal yellow star. They'll eventually bloat into a red giant. Then they'll puff off an atmosphere, try to kickstart a few nuclear fusions, and then become a planetary nebula. If it's a more massive star, it's bluer, hotter, so its temperature, luminosity is much higher, so it'd be higher up the graph. That goes off into a red supergiant because it's a much bigger star to start off with. And because they can carry on with burning greater nuclear fuels of different sorts, they eventually become unstable and blow themselves to pieces and become a supernova. And if you on this Hartsprung-Russell diagram, it basically plots the path of stars of different mass that become hotter, brighter, and end up either becoming a planetary nebula or a supernova.
Yeah, I think you showed us the Hartsprung-Russell diagram in the supernova talk. That's where we saw it. So
that's right. Yeah, and they first found.
Go back to it. There's a PowerPoint actually in the Facebook page of Bob's talk on supernova, and the diagram is in there.
The work that was done on the Hartsprung-Russell diagram was done on globular clusters, because basically you have a ball of stars that are pretty much all the same distance away. So you can see from their luminosity and their temperature, the bigger the star, the brighter it is, especially if they're all at the same distance. A big bright star is obviously a bright star that's the same spectrum as another star that's dimmer is obviously bigger because it's like different light bulbs. So when they plotted all the stars in the globular cluster, they found that they had this pattern, and that's the Hartsprung-Russell diagram. And it's only because the stars are all at the same distance that they compare luminosities and the spectrum and then work out temperature luminosity curve. So it was all done quite ingenious actually, but that's how they did it, using a globular cluster as a standard marker for distance. So yeah, and as you say, if you put Hartsprung-Russell, you'll come up with quite neat things, and they'll actually show the paths of various globular clusters because some clusters are quite young, some are old, and other stars have moved on. So some globular clusters, the newer ones, have lots of low down main sequence, and other clusters that are very old are virtually all red giants, and it's quite interesting to see the difference of them. So look, yeah, look it up, Hartsprung Russell. I think I didn't write it down anywhere, did I? No, but yeah. Where was I? Right. The large bright diffuse emission nebula. The large bright diffuse nebula associated with hot young stars in star forming regions. The illumination here is the result of emission of light at various wavelengths by gases being ionized by ultraviolet photons from the very hot, massive young stars. Yeah. The nebula's color depends on its chemical composition and the degree of ionization. Most nebula have a very nice salmony pink red color, and that's hydrogen. So hydrogen is the most abundant element and is easily ionized, hence the most prominent color, and is responsible for the predominant red glow, usually H alpha, that is most characteristics. If the stars are very energetic, then oxygen, nitrogen, sulfur are ionized too, and that gives the blue and green emissions in the nebula. But most nebula are 90% hydrogen emissions, so most nebula are pretty much red. The elements that have been ionized are recognized by the emission spectrum, which give a signature spectrum of bright lines that is unique to each element. Still okay so far?
Yeah. I'm just gonna
Yeah.
screenshot that one.
Hello?
Remember that.
Yeah.
Yeah.
The emission nebula typically hundreds of light years across and will last for millions of years until such time as the gas is blown away by the radiation from the hot stars, leaving behind a spectacular open cluster, often containing hundreds, if not thousands of stars. Some, if not most of the hot young stars will die in the supernova and form a bubble within the nebula. Just trying to think of one, actually. I suppose the one of the Crab Nebula would, the Tarantula Nebula would be the best one, the one that blew up recently. Yeah. The examples of emission nebula, the North American Nebula, the Lagoon Nebula, Orion Nebula, Eagle Nebula, the Trifid Nebula, which we showed before, and down south, the Carina Nebula. And I'll just zoom this in now. Hang on a sec. There we go. That's the Orion Nebula. Do you recognize? This shows the red H, there's the hydrogen alpha emissions. There's the hot young stars that you can actually see have blown the gas out and dust in the bubble, which is quite nice. And we'll come on to this later, but it also is a combination of reflection and dark nebula. This is deceptive. I've got a crop version of this. That and that seem to be separate, but actually the dust is doing the bisection. You'll probably find, if you can see it from any other angle, that this glowing patch and that glowing patch are probably all one, and it's only our line of sight that appears to make it divided. So that's the Orion Nebula that we all know and love, and the trapezium in the middle, of course.
Yeah, so for our budding new astrophotographers, this type of nebula benefits from having an astro-modded camera where you've had the filter taken out and it's more sensitive to hydrogen alpha light. And it also benefits from having a narrow band filter as well, which basically cuts out everything except the sort of the reddish light that you want to see from these emission nebula.
Ironically, this is my Nikon D800, so not modded at all, that one.
Oh, that's good.
Yeah. Yeah, so if I use my Astro camera, all I can get is the trapezium. All I can get in is that much with my Astro camera.
But when you see images of that by other people, it looks a lot redder, doesn't it?
It does, yeah. I could really boost the red on this and make it, but I tend to think that looks quite nice.
Yeah, but, it shows the detail very well.
Really
yeah, let's go there. Yeah, so this is the M42 Orion Nebula showing the red H alpha emission lines. Well, in this case, salmon pink. It shows the gas being rumble out in a fan shape, which we got quite nicely. Most of the hot young stars you can't see. they're in this little lot here, and the infrared images show that there's thousands of them. So what we see is just a pale fraction of what's actually in there. And it's really doing its nut. And eventually that will be one magnificent, in 250 million years time, that'll be one hell of an open cluster. So take your vitamins, boys and girls. Right, so there's an emission nebula. The stars blow away the dust and gas, becomes a bit more mature, and you end up with what they call a reflection nebula. Ta-da! So reflection nebula, as their name suggests, they're visible through reflected light. Now, some brainy person, how do we know the difference between emission nebula and reflection nebula? Well, it's very easy. If you did a spectra of an emission nebula, you see lines in the spectra, purely lines. If you do a spectra of a reflection nebula, you see a broad, like the sun, you see a broad spectrum with dark Fraunhofer lines in it. So that is how you tell the difference between a reflection nebula and an emission nebula. The reflection nebula contains the spectra of the stars that's illuminating it, whereas an emission nebula contains the spectra of the ionized gases. So a good bit of thinking there by somebody. That's how you tell the difference between one and the other.
So they're not just blue and red then?
No, they're not just blue and red. No. The energy from the stars is not sufficient to ionize the gases, so that's the most important thing. So the gases aren't emitting, they're reflecting. But it's enough to illuminate the dust. The girls were like this, they got diamonds in them. This dust is composed of particles such as carbon, including diamond dust, iron and nickel. These two elements, the iron and the nickel, align with galaxies' magnetic fields. Hello. And so reflected light can be polarized. These elements come from supernova, which we'll discuss later, which have seeded the dust cloud. So they can learn a lot about reflection nebula by studying the polarization of the elements within them. That's several years worth of research there as well. Here's this bit. Reflection nebula identified as such by the fact that the spectrum of the lit dust is the same as a local star or stars, as opposed to the emission nebula, which is the spectrum of an emission nebula. Emission spectrum, which is of an emission nebula. The most well-known reflection nebula is the Pleiades. These are the Pleiades. I just about managed to fit it in. This is also a Nikon D800 shot through the 10-inch, I think that was. No, it wasn't. It was through the Vixen. That's through the Vixen because there's no coma. Yeah. Merope is this one. And as you can see, it's got quite, the dust is quite detailed. Another popular one, which Rakesh has imaged a lot, is the Witches Nebula. You've done that one, haven't you? I think.
No,
somebody
not,
had.
No,
somebody's done a. Is it John then?
Mark did the Witch's Head Nebula. Yeah.
Oh, it was Mark. Yeah, because he's done that. There's some beautiful shots of that. Interestingly,
Is the Pleiades actually classed as a nebula?
Yep, the Pleiades is an open cluster with an associated nebula.
Right. Okay. I just thought it was. I thought it was just classed as a cluster.
Yeah.
So.
Yeah, it's an open cluster, but it has a reflection nebula in it. Yeah. And in this instance, the dust it's going through is not part. Originally, they thought that the dust was the remains of the nebula that formed the Pleiades. But as time has gone on, they now realize it's just dust that's in space, and the Pleiades just happen to be going through it. So basically, it's a bit like the headlights lighting up fog. So the stars are lighting up the fog around them. So it's an open cluster with associated nebulosity.
Okay.
And that's why I've done it, because as an example of reflection nebulosity, it's very good. And you can see the streaks in it. Yeah. The Witches Nebula, which I mentioned before, is blue, and that's because it reflects the light of Rigel in Orion. So its actual color is blue. It's a reflection nebula, and it's blue courtesy of Orion. So as I say, this is M45, the Seven Sisters Subaru. And as I said before, once thought to be remains of dust and gas from which the Pleiades formed, it has since been found to be just dust and gas that the stars pass through and not related to the stars themselves. Merope is the star at the top left. And if I zoom, hang on a sec. And you can see that you can get a lot of detail. There's an awful lot of detail in the filaments. So say denser and more rarefied regions and around here.
Mm-hmm.
So it's a very complicated, but nothing to do with the Pleiades themselves. Apparently, computer simulations now, they reckon that the Pleiades once, about 100 million years ago, would have been in a nebula like the Orion Nebula. So 100 million years ago, they'd have looked like the Orion Nebula, and in 250 million years, they will have all gone their separate ways, so they won't exist as a cluster at all. So grab them while you can. Yeah, pity really, isn't it? Yeah.
Yeah.
Yeah, they're very hot. They're only 100 million years old. They're very hot and very blue, and most of them will probably blow themselves to pieces. So yeah. Yep. So that's Reflection Nebula, Dark Nebula. Yay. Yep. So called because they're dark. Yeah. Who thinks of these names? Good grief. Yeah. They are composed of very cold, 7 to 50 degrees Kelvin, just above absolute zero. Not yeah. You wouldn't want to go swimming in that. It's dense dust, but it's still only 300 molecules per cubic centimeter. Earth's atmosphere is 2.5 times 10 to the 19 particles per cubic centimeter. But in terms of astronomy, 300 molecules is dense. So quite a difference. So they're also called absorption nebula. They are typically about 150 light years across and contain the bulk of the interstellar medium. So yeah, cold. There's spectacular examples of the Horsehead Nebula. We know the Trifid dust lanes of the Trifid Nebula, the Orion Nebula, and the coal sack in the Milky Way, which is a massive block of dust that's blocking the background stars. Whereas most of the others are blocking emitted and reflected light. Interesting thing about the coal sack was in the early, when they first found it, they didn't think it was a dust cloud. They thought it was an area of space totally devoid of any stars. So they thought it was a hole, and they couldn't work out why the stars weren't in there. And then it was only as time went on, they suddenly realized, and they started doing infrared and could see the dust and gas. But they realized it wasn't a hole in the stars at all. It was actually a bloody great cloud that was blocking the stars behind them. So perceptions change over time. It was quite good.
I would have thought that initially, to be honest.
Yeah, no, as I say, it's only until they got new observation techniques that they, suddenly twigged. It wasn't that long ago that they thought the Andromeda Galaxy was a nebula within our galaxy. And of course, it's a totally different galaxy 2 million light years away. All of a sudden, space expanded a lot. There are giant clouds, 200 parsecs across, that 600, 700 light years. These are the giant molecular clouds. And then there are small clouds, Bok globules, at about 3 light years. The Bok globules are thought to be the possible precursors to protostar formation. So these Bok globules eventually will become the Herbig-Haro objects that we mentioned in the first instance. The Bok globules are found in star-forming regions, and the dust is extremely thick, but not compared to Earth's atmosphere. But it can be studied by infrared imagery. I've done a close-up here because of the Orion Nebula. That's from the other one. It shows the extensive dark nebulas, all this lot here. So this is like reflecting off massive amounts of dust, as you can see. And if you look carefully, can you see the, hang on, let's zoom in. You've got these as well, Martin, if you remember on your shot.
Yeah.
These round blobs and these there, all of those are Bok globules. So these are these could be protostars in the making.
Sorry.
Yeah, so, yeah, I get a number of times I've said planets as well, but of course they will form planetary disks at some stage. Yeah, so these are Bok globules, along with the giant dust clouds. So the Orion Nebula has actually shown us a nice bit, and because this is a bit of a close-up, you can see that this bit here is like a pancake coming out of the screen. And you've got illumination above and below, and I think it's an illusion. I think these two patches are joined, but the dust and gas is bisected the view. So you probably find from a different angle, this would be a lot more spectacular. So that's that. So there you go.
A different angle like Andromeda, do you mean?
Well, just 90, just not same distance away, but 90 degrees, looking at straight. If you look straight down at it, it'd be like probably look like the Arecibo radio dish all lit up like a Christmas tree. It looked like the Rosette and Helix, I think, if you look down it from the other angle. Yeah, yeah. Are you still all with us? Yep.
Yeah.
Yeah.
Right. So So we've said about stars. These are obviously new. We now go to the other end of the scale. Eventually. Whoop, there we go. So stars, all that we've done now is basically young stars that are forming or just formed. And then you whiz along to the other end of a star's life and they become planetary nebula. Yes, I did read about planetary nebula and I thought, how the hell do I condense this down into a lecture that doesn't last the entire week? They are astonishingly complex. It's only recent research that has sort of indicated why they are so different and sort of explaining why they have the multitude of shapes that they do and spirals and blobs and pointy bits. I mean, these are all my images, but these are the nicer ones, but some, of course, are incredibly angular and look like they're boxes. And it's taken astronomers a hell of a lot of research and computer modeling to work out what the hell's going on. And they're still not sure they've got it, but they're getting there. So where do you begin? They come in a myriad of complex shapes, colors, and appearances. They are typically 1 light year across, which did surprise me. And they last about 10,000 years. So all the ones we know and love in 10,000 years, won't see them. So we're privileged to, mind you, we probably see different ones instead. They would have come and new ones would have formed. They're formed from stars like our own. They're called main sequence stars, up to about 8 solar masses. And it's at the end of their lives when they've puffed up to the red giant stage and their nuclear fuel is almost exhausted. This is what will occur with our sun. It will form a planetary nebula in a few billion years' time. And although they look very spectacular when we see them from afar like this, if we lived long enough and survived the onslaught of a red giant, if we were inside the planetary nebula, it would look like a very faint case of light pollution. So it would just be an incredibly faint glow. We wouldn't actually appreciate that we were in the middle of a planetary nebula. The viewing angle and distance is everything. So having exhausted its fuel and shed its atmosphere, all that is left of the star and our future sun will be a white dwarf that for a time will literally be one of the hottest stars in the universe with a temperature from 25,000 to 200,000 degrees C until it cools down to nothing. And it's when it cools down that the planetary nebula disappear because they're not being excited anymore. There's no radiation to keep them glowing. So they'll be there in spirit, but not in illumination. The very hot central star is responsible for making the planetary light up as an emission nebula, ionized by the intense radiation for as long as it lasts. And you can see the central stars on all of these, actually. The Ring Nebula, that's that one. The Dumbbell, that's that. This is the Cat's Eye. And this one, probably most people won't know about it. It's the Bowtie Nebula. And the difference is the colors. So here we have hydrogen alpha and oxygen, ditto with the Dumbbell. The cat's eye seems to be mostly oxygen, so that's very, very hot and doing a lot of high energy excitation there. And the bow tie is mostly red. So that's basically mostly hydrogen alpha, which would suggest the sun's not quite as energetic and not ionizing quite as much. But and this is basically the sun's atmosphere, all puffed up and blown away, being lit up by the very, very hot central star in the middle. And this is a low surface brightness galaxy that is associated with the ring. Any questions on that?
Getting that red to show on the ring and the dumbbell is the trick, isn't it? It's quite difficult.
Yeah, on deeper images, of course, the ring and the dumbbell have about 10 different more layers.
Yeah.
The ring is the very small bit in the middle. The layers go out about as far as here, and ditto with the nebula, the dumbbell. It looks like a rose. If you actually see the whole of the ring, it looks like a rose with the ring smack in the middle and very tiny. Yeah. Yeah,
it's good to get the central stars showing as well.
Yeah, I managed to get two. I've got an AEA Altair Astro 183C. This was my first image I took with it, and to my surprise, I got both. That's the star that actually belongs to the nebula, but there's one that always shows that's quite faint, and I managed to get that as well, and the faint galaxy. So yeah, that was a bonus. I was quite pleased with that. Right, so that's what happens with stars that are up to 1/8 solar masses, like our sun. Anything above that doesn't puff up to become a planetary nebula at all. It blows itself to pieces. So, and that's a supernova remnant. Actually, I didn't go through the, never mind. So stars bigger than a certain mass blow up, don't follow the usual pathways. As I say, whereas our sun lives out its life at a sedate pace, lasting billions of years, before becoming a red giant and blossoming into a planetary nebula, much heavier stars live life in the fast lane. They squander their nuclear resources, synthesizing them, burning an increasingly exotic array of elements, from hydrogen all the way through to iron, getting much hotter, bigger, and brighter in the process until after a lifespan of only 10 to 100 million years, so very short-lived, or so, they end up producing the element iron in their core. This is the equivalent of nuclear ash. It can't be used as a fuel. So all of a sudden, and we did the talk on supernova as well, didn't we? So all of a sudden, there's no intense radiation pressure holding up the core. So in fractions of a second, the core implodes at 25% the speed of light, because basically there's nothing in the middle anymore, until the core's density becomes so dense that neutrinos, which can pass through light years of lead, just can't get out. The net result is that the whole thing rebounds and the star disintegrates into a supernova explosion. And depending on the mass of what's left, so when the star blows up, there's something in the middle, and depending on how big that something is, it'll either be a neutron star or a black hole. So, and you don't know until after the explosion what's left. And hopefully, I hope the link is working on this one, because I found a very nice image, video on the crab. Colossal cheat, but never mind. Famous and much loved examples of supernova remnants are the Crab Nebula, M1. That's the crab. Yeah, that's when I took. That's with the new camera. That's with the ZW0553C, that one. Their emission nebula due to the high energy radiation released from the stellar remnant, and in the case of the crab, something due to synchrotron radiation, where electrons are accelerated to near light speeds and their motion changes due to the intense magnetic fields, producing X-rays in the process, which obviously light up the nebula. The crab is famous for being the first neutron star pulsar to be detected. It pulses at 30 times a second because it's spinning at 30 times a second. So we've got a sun 12 miles across, what's left of a sun 12 miles across, spinning at 30 times a second, so you can imagine. its discovery was made by Jocelyn Bell, and for a brief period of time, it was wondered if the rapid cliques were the results of little green men. Yeah, hey. A hugely important result of supernova explosions is that all the rich variety of elements contained within the star and others made in the supernova blast are spread throughout the space. The shockwave from the supernova frequently causes nearby gas clouds to collapse to form new stars, which will incorporate the elements in their structure and then any planets formed around them. It's these elements that obviously help to make life on Earth. There's a very brief bit here on earlier stars. The earliest stars in the universe, so-called population 3, oldest, contain only hydrogen when they first formed, no heavy elements at all, because no heavy elements had been made. And then, of course, the hydrogen was converted into helium, and some heavier elements were formed. Those elements were then incorporated to the next generation population 2 stars, and those are the stars you find in the centers of most galaxies, the galactic core, same for ours. So our galaxy core contains population 2 stars, which are middle-aged, and they contain slightly more heavier elements than population 3 stars. And then when they go supernova, they seed population 1 stars, which is our sun, and they're in the spiral arms mostly. And they have a much higher proportion, again, of heavier elements on their initial formation.
Can I ask a question there?
Yeah.
You're saying about the second generation, population 2 stars.
Yeah.
This is going back, we're going back in time now.
Oh, yeah. So the population 3 stars would have been the first ones in the universe ever.
13 billion years, that sort of.
Yeah, that's it.
And what would the population 2 stars be, roughly?
I'm not sure. Whenever our galaxy formed then, so our sun's 4 million, so it'd be between less than 13 and greater than 4.
Yeah. Okay.
Yeah, and our sun's 4 million years old, billion years old, and they reckon that's a new one. Yeah. Most of the stars, so that as far as they know, I don't think there are any population 3 around at the moment, because they were very, very big, very hot, 200 times the mass of the sun. So they would have formed and gone in 100 million years ago, 13 billion years ago, and they would have started the process of creating the heavier elements. And then gradually other galaxies would have formed. They would have condensed, the central regions would be population 2 stars, which would contain some of the heavy elements produced by the population 3 stars. And obviously the galaxies were a bit more stable. And then the spiral arms, of course, are newer things that would incorporate all the elements that heavy stars in the core would have produced and blown up and seeded through space to create our stars. And when a population 1 star explodes, supernova goes off, there'll be a hell of a lot of heavy elements in that, much more than we've got in our sun. So the stars formed from the elements of population 1 star going off will be very rich in heavy metals, and who knows how they'll burn or what they'll form, because they haven't formed yet. So they're still working on it. So a few facts on the Crab Nebula. It's 11 light years across, so that's 11 light years. It's expanding at 0.5% of the speed of light. It exploded in 1054 as a bright naked eye object. What's left is a neutron star, a mere 12 miles in diameter, and a teaspoonful of it would weigh several million tons. So pretty good going. Right, I'm now going to see if we can find, get out of the way. And I'm going to see if I can get a link to this video. So last but not least, variable nebula. This is going back to the very beginning of star formation. All nebula vary, but in a timescale beyond human comprehension, usually. Variable nebula change rapidly. So you could take a picture this year, and if you took a picture next year in 2 years' time, it would look different. So you can actually see the changes. The most famous is Hubble's variable nebula, which I photographed 40 years ago and was hoping to photograph this year, but of course the clouds have been in the way the whole time. First discovered by Edwin Hubble, it caused a lot of debate initially as to what causes the rapid changes observed, as nothing can travel faster than light. It was then realized that the nebula was actually a reflection nebula and around a very young star surrounded by dense clumpy clouds of dust, which isn't actually, it looks like it's visible in this, but what you're looking at there is an intense reflection, not the actual sun. And the dark patches that were seen varying are actually the shadows of dust cast, obscuring the light onto outer parts, the dust and gas. And as these dust blobs orbit round the star, their shadows move against the nebula. So of course, and as they're not physical, they can move faster than the speed of light, or give the illusion of moving faster than the speed of light. So that was the mystery solved. They are very fleeting from a cosmic point of view. As the dust is blown away, the show comes to an end. So once all this dust and gas is gone, you'll just have a very bright star and hello, and nothing else. So Hubble is a good object to image, as is in the constellation of Monoceros. So it's a good current object. You can image that quite nicely, which I'd like to. This is Hubble's variable nebula then. Yeah, except all. Here it goes, and you can actually see it move. Can you see that?
Yeah.
Yeah.
Can you see the changes of the dust? Obviously, there's areas when it's not visible.
So how long of a period is that where it's changing? Is it a couple of years or?
It'll be over a couple of years, yeah. So hang on, there's a black and white one which shows it quite well as well. See? So. I think those are days at the bottom. You can see the variation. But yeah, so you can actually see it change. Oops, cheers, thank you. So there we go. So I'm screen share. Right. I shall stop sharing then.
Okay.
There we are.
Well, thank you.
Yeah.
Yeah.
Well,
thank you.
I can't pretend to have understood all that, but certain bits of it I do. And it gives me future reading to do on certain bits of those keywords that have come up.
There'll be a written test at the end of the week. Yeah.
So it might be interesting in the future if Betelgeuse goes supernova, might it?
Yeah. Oh yeah, that'll be that'll be up close and personal, wouldn't it? Yeah.
How long? I think we'd see that quite some time in the sky as well, maybe like a good few.
Oh
months.
yeah, that would last probably a couple of years. Something like that. Yeah, because the Crab Nebula lasted a good few months. Yeah, you could see it in daylight.
Oh, imagine that.
Yeah, yeah, it was a bright star in daylight.
Martin gets cross when it's full moon. Imagine if we had a big supernova for 2 years.
Yeah.
Nobody gets no photography for 2 years.
Yeah.
I'm putting my stuff on eBay now.
Yeah.
We'd be all right, Paul. We'll stick to planets.
Yeah. You know, I was going to say, Martin, you know, I got this new camera. Do you want to see what, because Facebook doesn't do it much justice, do you want to see what the moon looks like through it on a proper screen?
What do you mean now?
Yeah, I can do it now if you want.
To. Yeah.
Zoom might not do it justice either, right?
Hang on a sec.
That's pretty
can
good.
You see me? No.
That's impressive.
Yeah, that's brilliant, isn't it? Yeah, that's one of my better ones. Yeah, yeah. I'm going home. Oh, there we go.
Oh my God, look at that detail.
Can you see that?
Yeah.
Incredible.
That's the chip.
Yeah.
This is just one shot. This is just what you get. I couldn't believe it.
Is that with your new camera?
That's with a new camera. Yeah.
If anybody's interested, Andy Burkett's selling one.
Yeah.
Is
Yeah,
he still selling it?
It's a 553C. Yeah, and this is just one shot. I couldn't quite get the other end of the limb on them. So, but yeah, I was bloody amazed. I thought I'm only going to be using it for deep sky, but if I want to,
do you think are the Maria as flat as they look?
Yes, apparently
they look really, really smooth and flat, don't you? Like, almost like a plastered wall.
Well, they're lava lakes, aren't they? Essentially,
well, yeah.
basalt lakes.
Yeah, so
yeah.
They will be flat, but you can't. I just wonder whether there were any sort of marks in them at all. That it's just.
Oh yeah, they got little craters and ripples. They got ripples, where the because of course basically things sloshed, and then.
But anything that's liquid would actually eventually just reach a level, wouldn't it?
Oops, wrong one. Ignore that.
Molten.
Yeah, so apparently it does slosh a bit, and so they do have ripples. 18. And then a planetary camera does this. Hang on. So that's what a planetary camera does. So this is the camera I usually use for planets and craters, and that's Clavius. So you can sort of see the difference between the tiny chip of my planetary camera and the large chip of the new 553C with its inch square chip. So yeah, it's quite a difference to see the difference. Quite, yeah. So
yeah, they're excellent.
Yeah, so that's that.
Yeah.
Well, thanks very much, Bob.
You're welcome.
Thanks, Bob.
Thank you.
Thank you.
Stop sharing now, and then you can get back on. Yeah. So.
Obviously, Bob clearly knows his stuff with 40 years' experience of doing this, and way beyond me, for sure.
I wish. Yeah.
I really appreciated that with the Crab Nebula. My first ever hook that I got was looking at the Ring Nebula and the Crab Nebula on the French Riviera. For the first time I'd ever looked in a telescope, and they showed me the Crab Nebula and the Ring Nebula, and I've been hooked on the crab ever since. I just think it's absolutely stunning. So that was quite enlightening. To learn so much about it.
Yeah.
John's got some pretty good ones of the Crab Nebula now, haven't you, John?
He has, yeah. He actually gave me a printer. His first print that when we said, I think he did it. I don't know where he did it. If he did it even here, perhaps, maybe not. But I've got the print proudly.
One time.
Was it here, John, that you did that shot of Nebula of the crab or not? No.
Well, I've done it 3 times now, so I can't remember. I know the one last night. The sky was really clear. And, the
Tracking shot.
Light pollution over Blackburn, which is quite bad. But
well, you've started processing an astral pixel processor now, haven't you? And your shot's looking incredible.
Oh yeah, it's really good. Is that? Yeah.
Yeah, that one of mine was the Crab was astral pixel processor. When it finally decided to put the flats on.
Yeah, mine handles them perfectly. It doesn't give any problems.
Oh, I've done others with it, but for some reason this time wouldn't accept the flats at all. They kept telling me they're the wrong gain and the wrong exposure. Well, they are, because of course you don't do the flats at 100 gain.
Actually, the flats I used today were flats that I took in December.
Yeah.
So it shows that you don't really need to do your flats immediately. And you don't
provided that you got the same focus though, otherwise you're stuffed.
Well, secret to that is put a line on your focus it so that you don't move it.
Yeah, mine's motorized. The other thing is, of course, if you've got any extra dust blobs in the time in between or other marks, then of course you won't have allowed for them, so those will still show. That's why they tend to do flats in real time. Any dust blobs.
Speaking of calibration frames, you do realise that Chantal's invented a new one. We've got darks and lights, and we've got bias frames. We've now got hats as well. And hats are just like darks, except you put a hat over the end of it.
That's right, yeah.
Yeah, that's what I usually do when I'm doing darks. I usually put the end cap on and then stick my hat over it.
Yeah.
I put like, you know, like the case that your heater goes in for your lens, your dew heater. I put that like tie it around the back to like block the viewfinder, so it's completely black. I'm like, don't turn the lights on.
That's it. Yeah.
It's all good fun.
Yeah. So as I say, I had been pleased with Astro Pixel Pro so up until my Crab Nebula, and then, as I say, I had to do the one part in the Astro Pixel processor and then apply the flats in DSS, and it worked. And then for some reason, I just had another go with APP, and it accepted them. But no reason why I've no reason why out of 5 times it just refused point blank to incorporate them. But never mind.
That's how it goes sometimes.
Yeah. Well, unfortunately, too many things go too often, and you tend to get a bit fed up with it, then, don't you?
Yep, yeah. Been there, done that.
Right, well, if you guys get fed up, then how do you think us newbies feel?
It's
exhausting.
Sometimes it drives you crazy, and sometimes it just goes so sweet. You just wonder what the problem is.
Yeah. I think probably as you do it more often, you expect to have more consistent results, and when that doesn't happen, you get frustrated.
Yeah, definitely.
Come and say hello, because they all heard you.
Oh,
there you go.
Hello.
Yeah, hello. Yeah. She's got a voice like a banshee when she lets rip, but yeah. Good, she'll, yeah.
Well, I took a few good shots with my Batonov mask on the other day, wondering why they weren't coming out very good.
I've done that a few times.
Why? What's the answer?
Yeah, you definitely need to subtract your dark frames for that one.
The worst thing is just not knowing what's wrong with it when you're doing exactly the same thing the night before. You do it again, and something's not working.
Yeah.
Oh yeah, I know.
I had a short circuit last night on my main power to the mount.
Oh, no good.
Which wasn't good. I saw sparks shooting everywhere.
That's what blew my motherboard. So be careful with that.
Yeah, I switched it off straight away. What it was, the power pack, where it goes to comes out of the power pack to the mount. The 2 wires that come out had broken inside, and they were touching each other.
Yeah, that's exactly what happened to me. And it shorted, and then I was 6 months without the mount.
Yeah, it's fixed now. So
yeah,
I've just bought one of these small power packs that have an inverter in it, which I'm going to take to a dark site somewhere.
Have you been up to Bowland, John, recently, where the lay-by where those big trucks were?
I haven't. Have we been since the trucks? No, we haven't been since the trucks.
But you don't know if they're still there or not?
No. Did I go one? I think we went one time, but I was poorly.
Oh, you came back early, didn't you? Yeah, I remember that.
Yeah. I went and I was car sick, so I had to come home.
I'm just wondering.
It was a really nice.
I think that spot in Bowling is a good place for us to go, but we'd want to probably get about 4 or 5 cars there, and we couldn't do that with those trucks there.
Yeah, there is another spot that I've found. I haven't tried it out yet, but I've looked at the horizons, and it looks pretty good for the most objects, and that's the Entwistle Reservoir, because it's got a road between on the dam, and it's a really wide dam, and it has 2 car parks, and it's really dark.
Right.
What about the trees?
Well, there's plenty of trees, but the trees are not in the place. They're in the not important areas.
Yeah.
Mm-hmm.
But that's pretty dark. I'm going to try that out one day or one night.
Okay. Well, we're well over the 2-hour mark now, so I'm going to say thanks very much to Bob. That was a great presentation. I'm sure we'll have the PowerPoint for that, so you can have another look at it put onto the Facebook group. There's a file section in the Facebook group where you can put PDFs and PowerPoints and things like that. So there's a few things in there. Bob's presentation is going there, and Ken, who's said goodbye, but he'll upload his to there as well, so that would be good. And I'm sure you can watch some of those links and videos and things, perhaps a little bit smoother if you run it on your own computer rather than through the Zoom. I think we're going to have to think about when we do PowerPoint presentations with videos in what the best way of doing it is. I mean, that way worked with Bob just then. But when I do it, I actually download the video to my computer and build it into the PowerPoint. And that seems to work all right. I think it's going out to web links that makes it a bit difficult. But anyway, has anybody else got anything that they want to say, or should we just? No. So thanks very much to Rick for hosting this for us again on his work account.
Yeah, cheers, Rick.
It allows us to have more than the 40 minutes because they cut you off very quickly.
Oh, thank you very much indeed. Yeah.
And great to see everybody, and great to see all the new people. And I hope John and Chantal and, well, Roy seems to have gone now, but I hope you all join us again sometime soon. Okay, so good night for now.
Yeah, brilliant. Thanks for
Nice to meet you.
See you later,
everybody.
Bye.
Bye.